We can use the same crystal field theory electrostatic logic that we used before to figure out how we expect the d orbitals to change in a square planar field. So if we start with our degenerate d orbitals, and we think about what would happen if we had a square planar ligand set, then we're defining the z-axis as being sort of up and down here because it's going to be the same as the C4. And then we imagine that the ligands are on the x and the y-axis. So that should be important for you. The ligands are along the x and y axis. So that means that we can at least guess the highest energy orbital. That's going to be the x squared minus y squared orbital because it's pointing directly at the ligands. The next highest orbital is going to be the z squared because even though it there's no ligand along the z-axis, the z squared has the torus, the donut, that is at least partially pointing directly toward the ligands. But there's going to be a big gap between the x squared minus y squared and the z squared. The next ligand is probably the dxy because it's pointing in between the ligands, but in between, like sort of in the same plane where they are. And then the lowest energy ligands are probably the xz and the yz. In the D4H point group, those orbitals are degenerate. We can see that from the character table, D4H. And we're going to say that they're the lowest because they're pointing between the ligands and they have some component in the z direction where there are no ligands. Now, I keep saying like probably because while it's pretty clear that the x squared minus y squared is the highest energy orbital, the energies of these lower orbitals, especially of the xy and the xz, those can change, and it depends a little bit on what the ligands are. I'm not necessarily expecting you to be able to predict when it's going to be one way or the other. That's something that we would have to determine via some kind of measurement or some sophisticated calculations, but maybe you can be comfortable with the idea that there's a little wiggle room between which of those are actually lowest. Okay, so if we imagine here is our electron configuration, then maybe it becomes clear to you why this geometry is the most common for D8 electron counts. Also D7 and D9, but D8 is kind of the poster child here. So let's think about that. If we were to fill in our electrons, 1, 2, 3, 4, 5, 6, 7, 8. Look, we fill all of those lower energy orbitals that are stabilizing our electrons, and we don't fill that highest energy orbital. So basically what we've done, we've said, okay, x squared minus y squared orbital, you be way up there in the sky. But it's okay because we're not actually going to put any electrons there. So it's really common for D8 complexes to be square planar. Also common for D9. So D8, first row, that would be nickel 2. But you also see this quite a bit with copper 2, D9 complexes, because then you put an electron in that highest energy orbital, but only one electron. And so that results in an overall lower energy configuration.